Okay, so the precipitate rapidly turned from white to brown in contact with air, so it must have been manganese. And now look at the test of Fa1C which has been already written, that it forms white precipitate which dissolves in excess aqueous ammonia to give a colorless solution. And you are doing the test with silver nitrate, isn't it? So test with silver nitrate means test with silver means test of halogens, isn't it? So look, so chloride, it gives white precipitate with silver which is soluble in aqueous ammonia. So Fa1C must contain manganese, it must contain manganese and it must contain chloride ion. Okay, now that last question said, write the formula of all the precipitates that you have observed or that are already written. It's a dirty green precipitate here after adding sodium hydroxide, so it must be a hydroxide precipitate, and the ion present was iron 2 plus, so one precipitate is iron 2 hydroxide. Okay, here we have obtained a white precipitate after adding barium, so it must be barium sulfate. Okay, then we have obtained a dirty green precipitate after adding sodium hydroxide, it's a hydroxide. So, and the ion present was chromium because it dissolves in excess, but the candidate has not written that, so it must be chromium hydroxide, chromium 3 hydroxide, CrOH3. Here we have obtained a white precipitate which rapidly turned brown, and this is manganese, so the precipitate must be manganese hydroxide. And after adding silver we have obtained a white precipitate. All nitrates are soluble, so nitrate cannot form the precipitates, silver will form the precipitate, so this must be silver chloride, isn't it? Because it's a white precipitate and it must contain chloride, so the precipitate is silver chloride. This is how to write the formula of the precipitates, and that's what has to be the answer here. Okay, so now the second question. In this experiment you will choose a reagent and carry out test by yourself to identify the chemical radicals present. The compound label Fa2 may contain any of the following. It may be sulfate, it may be nitrate or nitrite or carbonate or chloride or barium ion. Okay, so it said that you have to prepare a table and write possible observation, but you should not carry out the test. So just choose reagents from the reagent table, write the name of the reagent and write a possible observation. Like the candidate has written that well for sulfate, well for nitrate and nitrite, but he didn't differentiate between nitrate and nitrite. Nitrite has to be differentiated by adding some acid, dilute acid, after which it will liberate brown gas. So this should have to be written here. Look, with sodium hydroxide and aluminum foil, not only with sodium hydroxide, you also have to add aluminum foil. With sodium hydroxide and aluminum foil, both nitrate and nitrite will liberate ammonia, but nitrite specifically gives brown gas when dilute acid is added, which is not in the case of nitrate. So that has to be written here. Okay. Carbonate, add dilute acid, carbon dioxide forms white precipitate soluble in ammonia, that's all right. Barium, add sodium hydroxide, faint white precipitate form. But for barium, just always remember that it's better to add any kind of compound containing sulfate or sulfide, because you will get a white precipitate. A faint observation or a weak observation sometimes does not convey the mark, so it's better to test barium by using any solution that contains sulfate or sulfite. But this is quite okay because this observation is written in the observation table. Now carry out the test of sulfate ion. For sulfate ion, the candidate has added barium nitrate, after which white precipitate was formed. Okay, now the question said By observing appearance of Fa2, explain how you could understand that either barium it should be that understand that barium is absent from the mixture. Now look at the appearance of Fa2. This is Fa2, isn't it? This is Fa2. So Fa2 is a clear solution. You cannot observe any precipitate here. It's a clear solution in this case. So the candidate, you have done the test for sulfate and you have got white precipitate, isn't it? So this solution contains sulfate. Now if the solution also contains barium, then barium and sulfate are present in the same solution. There must have been the deposits of some precipitate over here, okay, but look, there are no deposition of precipitates, isn't it? So this solution, since you have identified the presence of sulfate, so this solution must not contain barium, because if it do, then the barium and the sulfate, they must have produced they must not have produced this colorless solution, because barium sulfate is a precipitate, which may be the test for sulfite or barium. So since this solution contains sulfate, so this solution does not contain a barium ion, because the solution is a clear solution, isn't it? This will be the answer. Now let's switch to question number 3. Okay, look, in question number 3, the crossed out boxes are the boxes that you will not be using to do the test. So you have to add first small amount of solution in the left column and then add solution from the top row. Okay, so we will take Fa3 and we will add Fa3D. So here I am taking a test tube. I'm taking Fa3A. It's a clear solution, and I'm adding just 2 drops of Fa3D. Look, we have obtained a, it's not red brown, isn't it? It's a completely brown precipitate. Okay, it's a completely brown precipitate. Okay, so the candidate has written that brown precipitate is formed, but since all the solutions are unknown, so we better do some further test, because in the table we have red brown precipitate, but we don't have perfectly brown precipitate, but the precipitate was perfectly brown, isn't it? So we better carry on doing further test. Now we will be adding Fa3B with Fa3D, isn't it? Okay. So Fa3B with Fa3D, isn't it? Okay. It's a kind of white precipitate, but it's, yes, it's a white precipitate, but it's kind of getting dissolved. Let me add some more Fa3. Yes, it's kind of getting dissolved. So a white precipitate is formed and it's getting dissolved. If I smell the solution, it's like a bad smell of ammonia is coming. So let me see. Smell of ammonia. So it must contain ammonium hydroxide, because it's ammonia smell. And Fa3D, buddy, I'm not sure what you are. Okay, so now we will be adding Fa3C with Fa3D, Fa3C, Fa3C with Fa3D. The two drops, 1, 2. Okay, so we are getting a white precipitate here, isn't it? So it's a white precipitate after adding Fa3D. So Fa3D is producing a brown precipitate and then a white precipitate which was slightly dissolved, and now we are again getting white precipitate after adding Fa3D with Fa3C. Okay, so let's write it out. It's white precipitate with Fa3C. Okay. Now the other test, the Fa3B with Fa3A. Okay. Fa3B with Fa3A gave no precipitate. Still I'm getting the smell of ammonia. So Fa3B must be ammonium hydroxide or aqueous ammonia, because it's giving a smell of ammonia by itself, not even by heating. Okay. Okay. So now Fa3A with Fa3C. First let me take Fa3A. Okay, just reducing the amount. Sorry, it's Fa3C I've taken. Now I will be taking Fa3A. It's giving a white precipitate, isn't it? It's giving a white precipitate. Yes, it's giving a white precipitate. White precipitate. But since no amount is specified, so I will be adding excess of the precipitate, I mean the solution. Oops, it dissolved. So with few drops it's a white precipitate, but it dissolves in excess. Okay, alright, let me write it down. So look, with Fa3C we have added Fa3A. A white precipitate was formed, but it dissolves in excess, isn't it? So the candidate has just written that white precipitate is formed, but he didn't write that it dissolves in excess. In this case, now we will be adding Fa3B with Fa3C. Let's see. Oh my god, that hurts. So Fa3C. Okay, I'm taking a small amount. Now I will be adding Fa3B, and Fa3B is ammonia. We have got the smell. Okay, let's see. Look. Oh, it's a white precipitate. Let me add excess. Oops, I think it's getting dissolved, isn't it? Let me add some more. Oh, it got dissolved. It all got dissolved to give a colorless solution. So with ammonia, we have got a white precipitate initially, but later on it dissolves in excess to give a colorless solution. So sometimes smelling the solution also helps to identify the solution, isn't it? Okay, so we are done with the test. So the candidate has done a mistake again. He just wrote white precipitate, but he didn't add it or mention that what will happen if excess is added. Okay, so let's go to the observation table. So Fa3B is aqueous ammonia for sure, isn't it? Because we've got the smell, and in both these cases white precipitate is produced which dissolves in excess. Now let's go to the analysis table. Here there is white precipitate, but nothing indication of excess is mentioned. It's like excess is strong acid, that it's a different reagent. But in our cases we were adding the same reagent. We were adding the same reagent which later on dissolved in the same reagent, but here they are using barium and then using strong acid. So these are not the cases. Let's turn over here. We have got white precipitate, okay, which is soluble in sodium hydroxide but insoluble in ammonia. So insoluble in ammonia, our white precipitate was soluble in ammonia, isn't it? Okay, and white precipitate insoluble in excess. So this is also not magnesium. White precipitate soluble in excess. Oh, white precipitate soluble in excess, so it must be zinc in ammonia, isn't it? In ammonia, so it must be zinc. And in another case we have got white precipitate which is also soluble in excess. So in both cases it's soluble in excess. So this one is ammonia, but this one is, okay, so sodium hydroxide. So our another solution that we were testing, here, over here, it will be white precipitate soluble in excess. It will be white precipitate soluble in excess, but we were sure that Fa3B is ammonia. So this is ammonia, this one is ammonia, so this must be sodium hydroxide, and this must have contained zinc. Okay, so Fa3A is sodium hydroxide, Fa3B is aqueous ammonia or ammonium hydroxide, and Fa3C contains zinc. Now this is a turning point, a trick. So Fa3A is sodium hydroxide, you have already identified, and with Fa3A you are adding Fa3D which form brown precipitate. Although this is not included in the analysis table, but just remember that perfectly brown precipitate is formed with sodium hydroxide only by the presence of silver ions. So Fa3D must contain silver since Fa3A is sodium hydroxide. Okay, so Fa3D is a solution that containing silver, maybe silver nitrate. And with Fa3C, the Fa3D, that means the silver, it gave a white precipitate, isn't it? And silver gives white precipitate with chlorine. So okay, so this solution Fa3C must contain chloride ions, isn't it? Okay, and Fa3D must contain silver because we are not sure about the nitrate ions. Okay, so Fa1A is sodium hydroxide or it contains hydroxide, Fa3B is aqueous ammonia or ammonium hydroxide, Fa3C is the zinc chloride, and Fa3D contains silver ions. And most of the silver salts are insoluble. So if you write also silver nitrate, which is the only soluble salt of silver, that will also be correct. So that's up to question number 3, and this is how you will identify the reagents when they're and when all of them are unknown. All are unknown, but in the past cases our reagent names were given, but here nothing is given. So you will just make the observation very carefully and compare it with the data analysis table given. Okay, now let's switch to question number 4. So question number 4 said nature by just heating it. So we will take it in a boiling tube, but I will take a test tube and heat it 2 minutes strongly. Alright, write the observations and the formula. Okay, so I am taking Fa4, just a small amount. Okay, and pour it carefully so that a minimum amount touches the wall of the test tube. Okay, just over here. Now I'm turning on the burner. Okay, just before doing the test, look, in the last day what the candidates did, that they just thrust the air directly into the solution, so that the precipitates here, look, these are all precipitates or impurities at the bottom, they all spread it out and the observations and readings were incorrect. So when you are doing a test with a reagent, if you see that there are precipitates at the bottom, do not disturb them, just press it, then put it over here, half inserted, do not touch the precipitate. Oh, I have disturbed them, sorry, so I will be taking from here. Okay, it's taken. Do not try to disturb the precipitates, and when you are putting the solution back, just touch it with the wall of the container, and that didn't touch. Okay, here, so, and pour it slowly like this, slowly. Okay, here. Okay, so now this time I will be taking test tube holder, and if you can see, okay, here I am heating the solution, here, can you see it? No? Okay, so I'm holding it like this and heating the solution. Look, it's turning black. It was green actually. Oh yes, it's turning black. A gas is produced from here. You can look at the sound. A gas is produced over here. Okay, so the gas looks colorless, isn't it? It's a white, maybe due to presence of water, but the gas is actually colorless. The test tube was brown. This test tube has got a permanent brown color initially, so the gas has no color. Now let's take the smell. No, it's not ammonia. So when you are heating a solid, there are some possibilities, like it may be carbon dioxide, or it may be nitrogen dioxide, or it may be carbon dioxide or nitrogen dioxide. Carbon dioxide has got no color actually, but nitrogen dioxide, NO2, it has got a brown color. In this case, don't be confused, the test tube was initially brown. It's not a brown color gas, but the gas we have found which were coming out has got actually a white color, or we can say it's colorless, because white color, because already water was present over here, some water was present over here. So that may be the evaporation of water, but the gas itself is colorless. So after heating, you're obtaining a colorless gas, so it must be carbon dioxide. So this solid is a carbonate solid. Alright, and look, the solid has turned black. It's a black solid that we have got. It's a black solid. So when you are heating a carbonate, it turns into carbon dioxide and the oxide remains. Like if you are heating sodium carbonate, you will get sodium oxide and carbon dioxide. So this must be an oxide remaining, and you must remember that an oxide which is black is for sure it's copper oxide. For sure it's copper oxide. Okay, so we have got, so our observations will be gas evolved. We will not do the gas test, but we will write it. So gas evolved that turns lime water milky, and a black solid remains. Black solid means copper oxide, isn't it? Okay, and the gas that were coming out, since it didn't had any color, so it must be carbon dioxide because we have obtained the gas after heating a solid. All right. Okay, so the formula must be copper carbonate, and just remember the color of copper carbonate. It is green. It's light green. Okay, now let's move on to question number 5. So this is an oxidation and reduction test. So first of all, to 1 centimeter cube depth of iodine solution, add 2 drops of starch indicator. Then that means after that there are some more tests. Okay, I will be trying to clean it later. So I am taking a test tube which is clean, and I am adding iodine. Okay, this is iodine, and I am adding starch in it, isn't it? Oh, it gave a purple black solution or precipitate, whatever you say will be correct, no problem. Or you can say blue black, no problem. So after adding iodine in starch, starch in iodine, we have got a blue black precipitate. Now it said at equal volume of sodium thiosulfate. Okay. Okay, so it turned colorless. So after adding sodium thiosulfate, it turns colorless. Okay. Now we will be taking some potassium iodide as the question instructed. It said 1 centimeter cube depth of aqueous potassium iodide solution and 3 drops of starch indicator. Okay, so potassium iodide solution and then starch indicator, we are taking 1, 2, 3 drops. Okay, so no changes observed over here. Now we are adding the equal volume of hydrogen peroxide here. So this was the volume that we have got. Oh, it's turning blue black. So starch is present and it turns blue black, so it must be iodine, isn't it? Because in the last test we have added iodine in starch in iodine, we have got blue black. So we have again got a color blue black, so must be iodine is present here. But initially, look, when you are adding potassium iodide with starch indicator with potassium iodide, we have observed actually no change, isn't it? So starch does not give any change with iodide, but starch gives a blue black change with iodine. So iodine has got blue black with starch, but iodide has got no change with starch. Okay, so the transition is from iodine to iodide, isn't it? Okay, now let's look what's going on. So here it was iodine, for which it gave blue black with starch, but when thiosulfate is added, the blue-black turned colorless, isn't it? That means for sure no more iodine is present here, but rather iodide is present, because with iodide the starch doesn't give any blue-black color. It also stated the change from iodine to iodide is reduction, whereas the opposite is oxidation. Look, here it was iodine because blue-black color, but when sodium thiosulfate is added, it turns colorless, although starch is present there. So sodium thiosulfate has turned iodine to iodide, isn't it? For which the color is lost. So it's a reduction reaction. That means sodium thiosulfate has reduced iodine, so it must be a reducing agent. Okay, because blue-black turns colorless, that's not a perfect answer. He must write that from iodine to iodide. And for hydrogen peroxide, look, it was iodide, for which with starch no change was observed, but when hydrogen peroxide is added, we have got a blue-black solution or precipitate. That means iodine is now present. So iodide was there, but it turned into iodine. Iodide was there, it turned into iodine, so it must be oxidation. And who did this? It's hydrogen peroxide. So hydrogen peroxide must be an oxidizing agent, isn't it? Okay. Now this one, you just need to carry out a prediction. Look, 1 centimeter cube depth of solution Fe2 plus, add sodium hydroxide. So sodium hydroxide with Fe2 plus gives a dirty green precipitate. Now when you are adding hydrogen peroxide, since it's an oxidizing agent, so it will turn Fe2 plus into Fe3 plus because it's an oxidizing agent, isn't it? So the color of the precipitate will turn red brown, isn't it? Like when the valency is becoming more positive, or valence is getting greater, so those reactions are oxidation reactions, and when the valence is getting smaller, those reactions are reduction reactions. Look, so Fe2 plus gives green precipitate, insoluble in excess, but Fe3 plus gives red brown precipitate, and hydrogen peroxide is an oxidizing agent, so it must convert Fe2 plus into Fe3 plus, increase in valency, which means it will be oxidized. And hydrogen peroxide is an oxidizing agent, so it must oxidize Fe2 plus into Fe3 plus. So that's what the question wanted. That what might be your prediction. So Fe2 plus with sodium hydroxide, it must be green precipitate, and where you're adding hydrogen peroxide, when you are adding hydrogen peroxide with Fe2 plus will get converted to Fe3 plus, and then if you add sodium hydroxide, you will get a red brown precipitate. These are the observations that you have to write. Okay, so now let's move on to our last question, the question number 6. So this is about organic compounds of class FB1, FB2 and FB3. So we will be doing test on FB1, 1, 2, 3, 4 tests. So I will be taking 4 test tubes at once. 1, 2, 3, 4. Okay, I'm taking them serially over here, leaving another behind. 1, 2, 3, 4. Okay, so first FB1 in all test tubes, and let's see what happens. So first magnesium, then sodium carbonate, then bromophenol blue, and heat with DNPH. Okay, so here is the 2 for DNPH. So we need heating, so I'm turning on the spirit burner again. Okay. Oh, it's gone. Let me bring some. It's a general rule that when you are doing tests on organic compounds, it's better if you just slightly heat the solution, because organic compounds are not all that much reactive. I mean, it's just a trick. Okay, so I'm adding some FB1 plus 1 over here, then small amount over here, then small amount over here, then small amount over here. So these are all FB1 classes. Okay, now first I will be adding some magnesium, but where it is. So just remember